pluses can interact with each other. And so they both interact. Resting attention here is going to layer 3, and ventral basal specific visual attention is coming into 4C alpha beta. And so that's how you could actually, for yourselves, for your own sanity here, you could actually write, because we're doing visual system right now, layer 3, 4C alpha and beta. But they're both being influenced by the particular nucleus. This is a moment in time where this is what we call in science a dynamic loop. I change you, you change me, I change you, you change me, the two of us together change each other so that our state changes moment by moment and we both cause it. And so this is a very complicated loop. And I tried to pick the easiest picture I could for it.
Can resting attention make amplified attention less amplified?
Oh gosh, yes.
And amplified attention, of course, can make resting attention more amplified.
Yes. You're absolutely, yes, they're dynamic with each other. Today, I was engaged in a deep state of road hypnosis on my way into work. And a car pulled out right in front of me. And when I mean right in front of me, I mean I was in the going straight lane and they were in the turn only right lane. And this person had no idea they were in a turn only right lane. And we were going into a 1-lane road and she just kept on going. Oh. And I did not process that for much longer than I would like to admit because I was somewhere else in space and time. And so yes, it can really affect how you process incoming stimuli. It took a moment for the reticular nucleus to go, hey, wake up. And then I had to go, what's going on? Why car there? At which point I panicked and nearly pulled into an oncoming car. We then thought I was the jerk. So here we are, back at our first moment. LGN here. Resting state, reticular nucleus coming in here. Although we both know they're both coming into both. They're going to move this information up and summate. And they're summating in a variety of ways. They're summating in more than one way. These pyramidal cells coming up might be inhibitory or they might be activating. They might cause exciting activations. They might make more, or they might inhibit things. Might be receptor, might be inhibitor, we don't know. This is where this part of the cortex does its job. It's going to do its math. Hey, is this something I should pay attention to? Now, in step 3, these in 4B and 3, and 6 and 5, then project output. And so 4B right here, this is going to our ventral and dorsal streams, as well as our long range attention networks. But these are going into the ventral, 4B is going to those streams. This is going to a variety of subcortical structures, among which is the thalamus, making this the corticothalamic loop piece. And so 3 and actually 6 is going out to the thalamus. And so we have, so they're sending information up and then back down. Over in 4B, it's heading out to other areas of the cortex. In 3 and 6, it's going back to the thalamus.
But they go down through like layer 5 and layer 6 and then up.
Yeah. Well, 4 does not go down through 5 and 6. I mean, it's going directly out that way.
Gotcha.
Now, that's the pathway through your cortex. So it goes up and then down, then up and then down, and then up and then down. At resting state for every person, about 8 to 10 times per second, maybe 8 to 12 times per second. This is happening when you're just at rest. It's happening a lot faster every time you process something visually. Here, neurons are firing thousands of times. By the time we get to this layer, because what we're measuring here is, for EEG, what we're measuring is actually the postsynaptic potential of layer 4, B, C, or 3. Long story short, that's what we're measuring. It's only firing 8 to 10 times a second, which means that's a lot of math going on in your cortex moment by moment, from thousands to 8 to 10 times per second. Yes?
So I know you said layer 6 is right on top of the white matter, and layer 1 is on top of what? What area is layer
It's
1?
on the outside of the cortex.
Okay, so you're going from like area 17 up to like area 18 and 19, or is all this in area 17?
All of this is in area 17. So, great question, because area 18 can be dorsal or ventral. So, it comes in area 17, it gets processed, and then it goes to area 18.
Okay.
And so that's exactly how it works.
Okay.
And the parvo bit goes to the parvo stream, area 18, and the magno bit goes to the magno stream. And so these are going on their way to the dorsal or ventral streams.
Okay.
And this one is going back to the thalamus. And this is why it didn't take me an instant, because I processed that something was wrong within 10 to 20 milliseconds. My brain knew something was wrong with that white car coming in front of me, but admittedly, it took me nearly 20 seconds to realize what was going on. Why? Because as the visual information was being processed into where and what was going on, I was getting this ping, and this loop here was slowly going, hey, you gotta do something. And so that was going up to speed until I was ready to engage. And so I wasn't activated enough to process information at first. I've never been my own fault. Yes?
Sorry for all the questions, but
This
so
is a
how
great-
does
these are
it
great questions.
determine how you go from like the thalamus and back that loop to going to the dorsal ventral pathways?
Quite literally, this is the most beautiful thing. People used to think that this was based on some sort of massive calculation we did, but quite literally, I hope, gosh, I hope nope, I didn't, because that would have been clever. Quite literally, it is, hey, the parvocellular cells go to 4C alpha. The magnocellular cells go to 4C beta. Then, because they went to that layer, they then go along those streams,
Okay.
quite literally. And then the thalamocortical loop comes in and out because it came from that loop.
Okay, so does like the summation of it determine like how signals are sent like to which areas after that, like whether the thalamus picks up more of the information from 4C, that layer, or like that way? Is that based on like the summation in the two
temporal
cells?
summation is the concept. Neurons fire all or none. So they're either firing or they're not firing. And all that happens is if enough are firing at the same time, the next neuron in the chain fires. We talked about that in a previous presentation, and we'll probably talk about it again, but it's just temporal summation. Now that tells you that a lot's going on. How many neurons are in area 17? We're looking at, in each hemisphere of area 17, about 140 million of them. And so that's a lot of summations right there. It's a very simple process. It's a lot of summations. If you take psychophysiology, you'll learn the pharmacology behind this as well. But for now, we're just talking about how the electrical part works. And right now, I'm just showing you the circuit. So let's get into, okay, shake it out. That was the hard part. Let's take a look at some EEG. In theory, in theory,